Hi, the delta rule learning is best algorithm to train the unthresholded perceptron to learn the weights through that it can learn the complex patterns. So here the predicted output for the linear unit can be calculated by using y dash equal to w0 x0 plus w1 x1 etc wn xn. It can be represented summation of I equal to 0 to n wixi. So here this can be represented by using the linear unit without threshold equal to y dash predicted output of the features x equal to w dot x. That means simply we can say wixi. Okay, so here the w is represented in the form of vector of values and x is also represented in the form of vector values. Okay, that's why we are representing w vector dot x vector. That's it. So here when can we use this delta rule for predicting the output and to reduce the cost in the given problem statement? So whenever we are getting the data set, we should identify the given data set is linear data set or non-linear data set. How do we identify that? The data set given in the table should be drawn using the plot. So in this plot I am drawing that given data points 0 comma 0, which is the having the class negative class. So I am using the green color dot to represent the negative class, and the sample number 2 0 comma 1, which is the positive class. Here I am using the 0 comma 1 this into mark, and the s3 is 1 comma 0, which is 1 comma 0 this one, so which is represented by using the into mark. Then and another one is 1 comma 1 here, which is negative class, which is represented by using the green color dot. So here we are having 4 data points in the plot. We should check, can we separate this data, that means classify this data by using the linear regression line or not. If you able to separate this by using linear regression line, that is linear decision boundary, then it is called linearly separable data. But when you are separating this one, this is classified correctly, but one of the data belongs to this into mark class is available in the another side, so which is not linearly separable line. And you can check in another way, so like this line. So here also the negative class, one of the negative class is not separated perfectly, so this is misclassified data. So this line also cannot classify the data perfectly. Then you can check with another regression line in this way. Here also this data is not perfectly classified, this is misclassified data, positive class. So we can check with another possible regression line here. So this another possible regression line is this one. So here also this data is misclassified. So whatever regression line we are using, that is not able to classify this data linearly, so this data set is called nonlinear data set. So whenever we are having the nonlinear data set, we can use the delta rule learning to reduce the cost, to give the more accuracy. So here the predicted output y dash over the features x representing the linear unit at the first phase, that means first stage of a perceptron which is having the activation function without threshold. So the error can be calculated by using least square error method 1 by 2 summation of I equal to 1 to m actual output minus predicted output whole square. So here m is denoting the number of samples. Here the principle of delta rule learning is to calculate the direction of steepest descent along the error surface. For example, suppose if I am having the plot like this, the error in the first iteration may be in the highest value, suppose here, then it has to identify the steepest magnitude it has to go towards the zero, that is converging point. Okay, so that is the aim of the delta rule learning. So here the direction can be found by calculating the derivative of error. That means we can calculate the gradients by applying the partial derivative on the error with respect to each and every parameter w we are going to use in the predicted output hypothesis function. Here this vector derivative can be represented by using, this is the gradient symbol over the error with respect to w is represented here for the each and every w. Here the gradient of the error with respect to w can be represented the first weight dou e divided by dou w0, then dou e divided by dou w1 second parameter, and etc. The last parameter is dou error divided by dou wn. So it indicates we are using n number of parameters in our hypothesis function. Since the gradient descent is representing the direction of steepest increase of error, here the training rule for the gradient descent is represented wi, that is new wi equal to old wi plus the delta wi. So the gradient we have calculated in the partial derivative. So the delta wi represented by using minus alpha learning rate into gradient of error with respect to all the parameters given in the hypothesis function. So this can be represented minus alpha into partial derivative gradient, in the sense we are going to apply the partial differentiation on the error with respect to each and every weight in the given equation. So here this minus symbol is indicating moving the vector movement of the vector in the search space. So here which is decreases the error with respect to the learning rate, which is always a positive constant though. So learning rate is already discussed in the previous videos. If you want, you can check that video. And the training rule is written using the following components. One is that update rule, weight update rule is new weight equal to old weight plus the delta of wi. So this delta wi is already we have discussed in the previous slide, minus into alpha into gradient of error over the all weights. This can be represented by using the gradient of all the parameters. So this dou e divided by dou wi, here what is the error formula? Error formula already we have used the least square error here, that is going to be differentiated with respect to wi. So 1 by 2 summation of I equal to 1 to m actual output minus predicted output whole square. So now when you are applying the partial derivation with respect to wi, so we can transfer this partial derivation for this two terms. So we are rewriting this equation. Then after that we are applying the partial derivation over this term. So 2 into actual output, so this is the exponentiation, this 2 into actual output minus predicted output into, then again we have to apply the partial derivation. This is with respect to the exponentiation, then this is the with respect to variables. So here dou divided by dou wi actual output minus predicted output. So again we are cancelling this 2 and 2, so summation of I equal to 1 this term, then this term is as it is we are using here. Then when you are applying the partial derivation here, the actual output is just a variable, but here predicted output is the equation y dash equal to wi xi. Okay, so that is the equation we are using here, wi xi. So when you are applying the partial differentiation over the actual output, we will get 0 minus, then when you are applying this wi xi, so minus w is here we are using the with respect to wi. So here xi is using as a constant, and wi you will get 1. So this is the term we are getting in the next line, so minus xi. So now we got the gradient of error with respect to wi, summation of I equal to 1 to m, this term actual output minus predicted output into minus xi. So finally we will get minus summation of I equal to 1 to m actual output minus predicted output into xi. So this is the uh, um, term we are getting finally by using the gradient rule and delta rule when we are applying for classifying the nonlinear data set. So finally we are writing the weight update rule, new wi equal to old wi plus delta wi. Delta wi is here we are returning alpha into dou e divided by dou wi. So dou e divided by dou wi is minus this term. So finally we will get, so wi equal to wi minus alpha into dou e divided by dou wi. So this is the final formula we are getting to update the new weights from the previous weights. When we are applying the gradient descent to search the search space to reduce the cost, the search space will be large or infinite hypothesis space that can be applied whenever the hypothesis space contains continuously parameterized hypothesis. That means the hypothesis is parameterized with weight parameters, and this error should be differentiated with respect to hypothesis parameters. That means error should be differentiated with respect to parameters given here. And there is some challenges in gradient descent. It has to converge to a local minimum sometimes, right? It is converging to a local minimum sometimes, due to it will make the converging a little bit slow. That means it needs more number of iterations. That means here if you are having the local minimum in the search space like this, what will be happen, there is the possibility of getting struck with this local minimum here, but our global minimum is available here. So the due to this strucking in the local minimum, it will take more number of iterations. If you take more number of iterations, the process will be little bit slow. If there are multiple local minimum in the error surface, there is no guarantee to reach the global minimum. So as we discussed in this plot, if local minimum is there, sometimes the gradient descent will stop the algorithm here, that it thinks there is no another global minimum point in the search space. So it will stop the algorithm once it reached the local minimum. This is one of the challenge in the gradient descent rule. So whenever we are having the nonlinear data set, we have to use the delta rule learning for the nonlinear data set. But if you have the linear data set, just you can go with perceptron with thresholded activation function. So here we are not using threshold. This is unthresholded linear unit for the nonlinear data set. For linear data set, thresholded linear unit will be used. This is the difference between perceptron learning rule and the delta learning rule. Thanks for watching.